It's a pleasure to be here with you today. So, my name is Pedro. I'm a software engineer working at CERN. And as you can see by the title of my talk today, I'm basically going to talk about two things. First, CERN, what it is, and then I'm going to say a few words about how we are doing monitoring over there. Just one quick note before I actually start. As you will see, my slides are this kind of old-style, classic slides, you know, bullet points, headers, footers, no funny pictures anywhere. But at least there's one good thing. The font size is more than 10, and I'm not using Comic Sans, so it's all good. Now, CERN. A few things about it. So it's an international organization. We are doing research on high-energy physics there. It was founded in 1954. This was right after the Second World War, and somehow in an effort to bring the European countries all back together. It started with 12 countries, and since then it has just been keep on growing, and nowadays there are 22 member states. There are a lot of collaboration with many other countries worldwide, including, for example, the United States, or, for example, there are other countries like India or Pakistan, Turkey, and Ukraine that have a special status. They are associated members, and we are working with them so that one day they will become full member states. For you to have an idea of more or less how big CERN is in terms of staff, we are more or less 2,300 people there, but actually we serve a much larger community of scientists which is spread around the world, which is more than 12,000 different scientists. So if we move on, where actually is CERN? So, let me move on here. Here we go. Over there, you can see these are the Alps, the mountains. Then you have a lake. You have the city of Geneva nearby. And then you actually have CERN. CERN is here. Basically, CERN sits between France and Switzerland. So this white dashed line here, this is the border between the two countries. On the upper side is Switzerland, on the other one it's France. And then you can actually see here, this is the main site of CERN. It's the site of Merin. Actually, this is where most of the offices are. My office is there. The site itself is also half in one country, half in the other country. So actually, my office is in France, and the restaurant is in Switzerland. So I just have to cross the border all the time. And then we have another site, which is really here, and this is the site of Prevsa, where actually the real construction happens. I also profit from this picture to introduce maybe it will help. This big yellow line there, it's our main project. It's the LHC, the Large Hadron Collider. This is basically a particle accelerator. It's a project that started many years ago, and recently, in 2012, it allowed us to confirm the discovery of the Higgs boson. An accelerator, thank you. As you can see, the accelerator is quite big. So it's 27 kilometers diameter. And then along the accelerator, both on the Swiss side and the French side, there are 4 main points, which we call the detectors, the experiments, where the collisions of the particles actually happen so that physics can actually be done. If you're curious more or less to understand how does the actual tunnel looks like, here you go. So you can imagine now we have a tunnel, 27 kilometers diameter, 100 meters underground. And why underground, you may ask? Well, for just simple reasons. First of all, if we had to build a tunnel at the surface, it will just be too expensive to buy all the land. And second thing, just because it's just easier to build it underground. So there's a tunnel, 3 meters wide, and then inside you have the superconducting magnets, which are these blue pipes that you see there. So actually, we're talking about 1,600 of those superconducting magnets, which are installed in the tunnel. Inside the magnets, you can see those 2 pipes there. This is actually where the particles accelerate, where the beams go. There are 2 of them. One goes clockwise, the other one goes anti-clockwise. And of course, at this phase in the accelerator, actually, the collision will happen in this machine here. So this is an example of our largest detector, the Atlas one. This is something like 25 meters wide, 50 meters long. Sorry about all these meters, kilometers. And for you to have an idea of the scale, there are 2 people that are actually working there, so you can see how big this whole thing is. And inside, in the middle, you can see where the particles are, and then the collision, we cross the beam there, the collision happens, other particles are generated, and then basically there are a number of different detectors all the way that will detect all the collisions. You can imagine that we are talking about a lot of data. And if I take again the example of the Atlas detector, here we have basically something like 40 million events being generated per second. This is really way too much. Something like, if we had to talk about data volume, more or less 1 petabyte of data. Of course, this is too much. So using hardware triggers, we start to bring this down, this number of events down, so that we have something that we can actually work on, and we reduce more or less the noise. We go down to more or less 100K events per second, which is still a lot. And then using some sort of online farms that are sitting right next to the detector and using software triggers, then this number goes down to 1,000 events per second, which actually we then want to store and record for study afterwards. And here we're talking about 4 gigabytes of data per second. Okay, keep in mind that this is one experiment, and I mentioned that we have 4 experiments like this. Well, not all are the same size, but. So if I move forward, of course, this data has to be stored somewhere. For this, we have our own in-house data centers. We don't put actually much of this in cloud. And we have our main site. This main site is built in the Geneva site. It was built in the 70s. You can see some pictures there. However, recently, 4 or 5 years ago, we started seeing that we were reaching some capacity, power capacity problems. So we decided to build or to use an extension site. This site has been located in Budapest, in Hungary, and it is connected to the CERN site with 3 100 gigabit links. Also important to mention is the fact that in both sites we use standard commodity software. For you to have an idea of the numbers, if I put together the Meyrin site and the Wigner site, we have approximately 14K servers providing something like 200,000 cores. Of course, all of them, they have a local disk, but in addition to the local disk, we also have tape storage to archive our data. And in our tapes nowadays, we have more or less 190 petabytes of data stored. Still, even if we have data centers, this is not yet enough. We actually want to process all this data. This data has to be computed. So for this, CERN started the worldwide the LHC computing grid project, WLCG in short. So WLCG provides a global computing resources and storage, distribution, and analysis for the LHC data. It's basically built on a tier model where you have the CERN tier 0 at the center that, of course, is connected to the detectors and it has all the live data. And then this data is distributed in different LHC sites that form some sort of tiers. So you have the tier 1, tier 2, and tier 3. Altogether, the WLCG is a global collaboration that has more than 120 sites that are spread around 42 countries in the world. So as I was saying, you have the tier 0 at CERN, which plays where all the data actually comes from. Here we do some sort of initial reconstruction of this data. And then we also archive the data, and then we start sending this data to all the different tiers. The tier 1s, which are basically 13 main other sites that exist. Actually, some of them are here in the US. They do also some sort of this initial reconstruction phase. They do reprocessing, and then this data can actually also be served to the tier 2s, where they actually are used for simulation or for end-user analysis. So by now you have more or less an idea of CERN, the data center, the WLCG project, so I can go on to the monitoring part. One thing that I have to say here is that we are actually not, my team, we are not actually working with the physics data. We are here only to provide a common infrastructure to monitor the WLCG, to monitor the CERN data centers. So what we actually have to provide is solutions to measure, to collect, to transport, to visualize, to process, and to alarm all this data that comes from the infrastructure that is the CERN data center and the WLCG coordination. So if we talk about now in terms of data size, I can push me for another one. So if we talk now in terms of data size and which type of data do we have, so we have a big variety of data, mainly a lot of metrics and logs. And if I have to categorize this data, basically there are 4 types of data. We have the data center metrics, basically hardware and OS. we have data coming from the IT services that run in the data center. And then we have data coming from WLCG, basically data from sites and services monitoring, and data from the WLCG main operations like job monitoring or data management. In total, this is more or less 500 gigabytes of data, of monitoring data that we have to process per day. It's a quite spiky workload. And of course, when things go bad, then we have even much more data and even much more users that we have to handle. Sorry, I'm back. In terms of the overall architecture, and following a little bit of the lines of what Megan was saying yesterday, we try to have, as much as possible, open source tools. We try to have a common solution that we can use both for the CERN data centers and for WLCG. And we try to have and to put all our focus on having an infrastructure that we can scale. If we have more monitoring data, we are fine and we can scale it. So that we can instead give the power to the users to create their own dashboards, to create their own views. And this way we can focus on actually scaling the infrastructure. We follow a quite standard approach where we have basically a phase of integration of data sources. Then we have to transport all this data in a common way. We may have the option of doing some processing. We then store the data in different backends, and then we have tools to access the data. Now, let me give a few more details about all these different areas that we are working on. From the sources point of view, there are basically two types. Either we have internal data sources, and here I'm talking about the metrics that come from the data center operating system or hardware. For this, we decided to go for CollectD. We plan to have CollectD installed in more or less 30,000 nodes with a sampling frequency of more or 1 minute. And then we also have the other type of data sources, which are the external ones, basically coming from the services that run in the data center from WLCG. Here we have to support a mix between push and pull models, and we have also to support different technologies and different protocols. This is some numbers I took at the end of last week. You can see that we have quite an heterogeneous set of data sources. So we have around 45 different producers nowadays, so it's really different types of data. Some of them are just a few megabytes, while in some cases, in others, they are quite large, and we have, for example, data from CollectD, which is more than 10 terabytes, or data from the FTS service. FTS is the main service of WLCG to transport the data, so file transfer service. Or, for example, we also collect syslog data, and we have more than 10 terabytes of syslog data stored in HDFS. So now we have all this data together, and we want to transport it. Here, we decided to go for two main technologies, Flume and Kafka. From the Flume point of view, we have decided to go and have some sort of dedicated Flume agents to actually receive the data. And this is actually where we apply these different, either we have push or pull models. We have Flume agents which are dedicated to talk with different protocols or different technologies. For example, we can get the data from a messaging broker because the guys from Atlas in the US send the data this way. Or we have another Flume agent that gets data from Oracle because some other guys in Asia have this data stored in an Oracle database there. And then we have a number of other Flume agents to get the data from either logs or metrics. All this data is aggregated in another Flume agent that then puts the data in Kafka. Data is buffered in Kafka, and then it can go along and be stored in the different storages. So, as I was saying, we have approximately 10 different types of Flume agents. And if you know a little bit of the Flume terminology, we have something like GMS as a source, Avro as a sink, in other cases, Kafka as a source, Elasticsearch as a sink. In all cases, we always use file-based channels, just because we want to have some persistency of the data there, but we don't want to have a big capacity. The big capacity of buffering, this is done at the Kafka level. We use a lot the Flume interceptors and morphlines. This is mostly for validation, for transformation, where we do some checks on mandatory fields or to apply some common schemas. As I was saying, from the transport point of view, Kafka is the rock-solid core of the transport layer. Today, we have the data there being buffered for 12 hours, even if we want to grow and have a target of 72 hours so that we can have a relaxed weekend. Each data source is stored in a separate topic in Kafka. Each topic is divided in 20 different partitions, and we have several replicas per partition. This is just another of our dashboards. This is actually the dashboard that we have for the internal monitoring of the monitoring. And you can see some plots about how much data, the rate of data that we have in Kafka, or for example, how Flume capacity is. Now we go for the processing. In some cases, we just let the raw data go. We just store the raw data as it is. In some other cases, we want to do something more with it. For this, we use Spark. And we basically have two categories of jobs. All of them, they are all Scala-based. We have jobs which are for stream processing. And basically here we do things like enrichment jobs, where we add topology metadata. For example, if I use the example of the FTS service I was talking about before, this is a service that has events that just says file A or event A was copied from site B to site C. It has all the metrics about the transfer itself, but we don't have more information about what is site B or what is site C, in which country it is. So we use this type of jobs to enrich the event with this other information. We have jobs which are just simply for aggregation. Mostly, sometimes we want to do aggregation over time if we think that the raw data actually doesn't really matter that much. Or we have other jobs for correlations when we want to check things between data sets. The other category of jobs that we have are the batch processing jobs. Of course, here data doesn't come from Kafka, it comes mostly from HDFS. And these jobs are used for doing compaction of the data, reprocessing of the data, and of course, the usual reports for the management to have a look. All the jobs, they are built and they are packaged as Docker images. So basically through an automatic process at every push using GitLab CI. The jobs are then orchestrated as processes in Mesos. We use Marathon for long-lived processes, like the streaming ones, and we use Kronos for just the standard recurrent jobs. And then the jobs get executed in Mesos, or in some cases they also execute in a larger Yarn cluster that we also have access to. And this is more or less for the processing. Now, if we talk about the storage, as I said, the data is all there in Kafka, and then using 3 dedicated Flume agents, we write down this data to the different backends. And here we use 3 main technologies: Hadoop, HDFS, Elasticsearch, and InfluxDB. HDFS is mostly used for archiving the metric data for long term and for data recovery in case this is needed. Basically, we keep there all the monitoring data forever. Well, limited to the resources, but for the time being, we are still good. We use Elasticsearch for mostly searches and data discovery. There, the data is kept for 1 month, because clearly this seems to be enough for most of the data discovery activities that we have to do. And then we put data also in InfluxDB for basically plots, dashboards, and actually the visualization. Data is kept for 7 days, but in addition to that, we also have 5-minute bins that are kept for 1 month, and then 1-hour bins which are kept for a bit longer, for 5 years, so that our users can have their historical views in case they need. In terms of how do we actually write the data, so all the data is written to HDFS by default, and we use some sort of a path like that where we put the data. And all the data is then aggregated more or less once per day in 1 gigabyte files, so that we make the managers of the Hadoop cluster happy. Then, according to basically the use case, according to the user, some selected data sets, they are stored in Elasticsearch or in InfluxDB. In Elasticsearch, we have 2 generic instances, one where we put metrics, the other one is where we put logs. And we basically put each data producer in a separate index. From the InfluxDB point of view, we have basically 1 instance per data producer. From the access point of view, we use 3 main tools: Zeppelin, Kibana, and Grafana. Zeppelin is used mostly for getting data from HDFS, for programmatic access to HDFS and the generation of reports. Kibana just to connect to Elasticsearch. And then Grafana is mostly used for the plots and for the dashboards on the data in InfluxDB, but in some cases we also have some data from Elasticsearch. I'm not going to go in more details about these 3 different technologies, but I just want to show you some examples of some of the dashboards that we have there. This one for example, here is used by Atlas for the job monitoring activities of Atlas, and it shows the 7 days view on the jobs that were executed by the Atlas physicists in order to run their models. And there are things like the type of job, or for example, how many cores each job is using, or what is the site where the job is running. From another example of dashboard that we have, this one here shows collect the data that we collect from all the OS metrics that we collect from the data center. Standard collect the plugins like CPU, network, memory, disk, and so on. Or another dashboard, this one was actually done by my colleagues from the cloud team that run OpenStack. And here they are basically monitoring how many the hypervisors, how many VMs are there, how many VMs have been created, have been destroyed, and this type of things. One more thing I would like to say now is about alarms. I only have here one single slide about this. Actually, this is something where we are still quite, we didn't actually advance much. We are still using our own old tool that exists, that was developed in-house. It's an old tool set, maybe with more than 5 years old. This was just doing, or this is just doing local alarms based on local metric thresholds. Still, we have some plans to evolve this, and we want to move towards maybe a multi-scope strategy. We still find the local alarms useful, mostly for having local actuators. Here we'll try to also profit to what Collective can give us. So if you have also any suggestion, I'll be happy to hear. But also we want to have the standard base alarms that we can define from Grafana, or in some more advanced cases, we want also to support alarms by running Spark jobs, which can be, in this case, a bit more service or user specific. Final 3 slides. The one thing I would like just to briefly also share with you is a bit more or less of the size of the monitoring infrastructure that we have. So basically, we run all of our monitoring services on OpenStack VMs. We have a project of 300 nodes there, and today we are running more or less these different types, so this different number of components. In some cases, we have Ceph volumes attached. And for the case of InfluxDB and HDFS, we actually don't run this on VMs, when we run this on physical nodes. Altogether, it's important to say that all the configuration here is done via Puppet. Final thing, a few lessons learned. So we are already running this new infrastructure for 2 or 3 years now, and we have learned a few things. First one that I find it quite nice was the fact that we decided to go for this approach where we have protocol-based Flume agents. The fact that we have one Flume agent which is dedicated just to get data from a messaging broker or from a database, this revealed to be extremely quite handy. It's very easy to add new data sources this way. And since, as you saw, we have so many different heterogeneous data sources, it's quite easy our daily life. Every time we have to import some new data set, we can easily do it. Kafka is definitely the core of the business. Before we actually start deploying Kafka, we spend some good amount of time to carefully plan the deployment of it. How many nodes do we have? How do we partition this? How we do for the topics? It's quite important to do this from the beginning so that we can scale Kafka as the project scales. And once Kafka was running, it's also quite important to actually have a good control about the consumer groups of Kafka and the offsets so that we actually no data is lost. Another thing that we discovered was, of course, as usual, that securing infrastructure takes time. We learned it once again in the hard way. We started with very few secure endpoints enabled, and then we decided to actually put everything secure. And of course, this was quite a long process. You can imagine first enabling secure endpoints in Kafka, changing all the Flume connections, changing all the Spark jobs. It was long, but we did it. Final things, from the Spark point of view, Scala was definitely the right choice. The data frames to decouple from the JSON marshalling, this was something seen as a good advantage. The fact that we decided to have checkpoints for our jobs in HDFS was also a good thing. But also important was the fact that we tried to keep the batch, the jobs, the code of the jobs as similar as possible between batch mode and streaming mode. This also is a nice thing. This way we can switch quite easily. We also had some very good experience with Marathon. It's a quite nice tool, and we were quite happy with it. On the other hand, with Kronos, things didn't work so well. And last thing was the fact that we have both backends, InfluxDB and Elasticsearch. From the user point of view, this could have been seen as a bit of a confusion. In the end, we try to take the best out of the different tools, and we try to make them as complementary as possible. So in the end, it worked out quite well. The infrastructure is there. and all our users are happy and they can have their dashboards run their jobs. So this is more or less everything I had to say. If you are curious about CERN, about how we do monitoring there, just feel free to stop me in a coffee or talk to me in Slack, and thank you very much.